So in this module, we're going to go ahead and start talking about electrolytic cells and electrolysis. We've talked a lot about voltaic cells and galvanic cells. Again, those are the same thing. They just mean they're a spontaneous process. The reaction just runs as designed. It may need a spark to get it to go, but once started, the reaction will continue until the reactants run out. In electrolysis, it's the opposite process. This is not going to go on its own. We have to provide electricity to it. We have to force the reaction to happen. This is like when you plug your laptop in to charge it, you're forcing a non-spontaneous process to happen. So we should be able to understand electrolytic cells and electrolysis, which is just the process, and be able to predict what's actually being oxidized or reduced at the anode and the cathode within a reaction. So again, in electrolysis, which is electrolytic cell, that's where it happens. Electrolytic cells are electrolysis processes. The redox reaction is non-spontaneous. The reverse reaction is spontaneous. So again, the reverse reaction is that voltaic or galvanic process. Because this is non-spontaneous, delta G will be greater than 0. So delta G is positive. The cell potential, E naught, is less than 0. Your cell potential is negative. Again, just completely opposite of that voltaic and or galvanic cell. The equilibrium constant K is less than 1. 0 is less than K is less than 1. So overall summary, delta G, your cell potential, and your K. Delta G will be positive, E naught will be negative, and K will be between 0 and 1. Note that both your cell potential and your delta G are related to the spontaneity or the driving force of a chemical reaction. There is a very important relationship between your cell potential and your delta G, okay? And we've talked about that some, we'll talk about that more. But that does tell you, will the reaction proceed on its own? So electrolytic cells. Again, in electrolysis, the reaction is non-spontaneous and electrical energy is required to force the reaction to occur. The reaction will not occur if we do not provide outside energy. Here are just two examples of an electrolytic process or electrolysis. One is the electrolysis of water, one is the electrolysis of molten salt. Let's go ahead and zoom in here on the water and we can kind of see what's going on here. We are literally breaking apart water, and I'll show you a YouTube video of that in just a minute. But we can see what's happening at the anode, what's happening at the cathode here. We've got at the anode 2 water molecules forming 1 mole of oxygen gas, 4 moles of H+ ions, and 4 electrons. What happens at the anode? Remember, you can either do anox red cat, or I like to keep my vols together and my consonants together. It doesn't matter. At the anode, it is being oxidized. Oxidation is loss. We're losing electrons, as we see here. So at the anode, oxygen is being formed. We are collecting oxygen gas. At the cathode, it's being reduced. Reduction is gain. We see here that it is in fact gaining electrons. 2 moles of water gain 2 moles of electrons, producing H2 gas and 2 moles of OH- ions, and we are producing hydrogen gas. We are literally breaking apart water. Water's not going to break apart on its own to produce oxygen gas and hydrogen gas, but if we supply electricity, it can happen. Other example we have here is electrolysis of a molten salt. Now, what do I mean by molten? Molten means melted. It means they're not ions. no water is present. The melting point of sodium chloride is 801 degrees C. Again, no water is present here. We can see here at the anode 2 moles of chloride ions reacting to produce 1 mole of chloride gas and 2 electrons. Again, anode, oxidation, loss of electrons, and that's what we see here. At the cathode, we have 2 moles of sodium ions gaining 2 electrons to produce 2 moles of sodium solid. We've got reduction. We've got gain of electrons. Again, that's what happens at the cathode, right? Our overall reaction here, 2 moles of Na plus, liquid form, react with 2 moles of chloride ions, liquid form, to form 2 moles of sodium solid and 1 mole of Cl2 gas. As a reminder to kind of help you guys, the little trick to remember what's going to be positive and what's going to be negative, notice here that my anode is positive now, my cathode is negative. So our little chart going to help. A and C for anode and cathode. E and V for electrolytic and voltaic. We put a positive in our first corner and the positive goes in the diagonal. This tells us what sign the anode and cathode would have under an electrolytic cell or a galvanic cell. The voltaic cell, same thing. This is what's causing it to happen in the opposite direction. We are literally forcing the anode to have that positive charge to it. We're changing the sign so that we can force a change on what becomes the anode and the cathode. Electrons still flow anode to cathode. So again, electrolysis, this process of using electricity to break a compound apart. And the reaction is still spontaneous. Electrical energy is always required to force the reaction to occur. The electrolytic cells can be used to separate elements from their individual compounds, such as generating hydrogen gas from water for fuel cells. It's another thing that is also common is recovering metals from their ores. Students often, or people in general rather, don't think about this often, but a pure metal, most metals, or I don't know percentage-wise, truthfully, but a lot of metals are not found just in their natural state in the real world, like out in nature. They're found stuck in rock, stuck in ore, etc. And we have to be able to pull those metals out, purify them to be able to use them for what we want. And so one way we can do that is electrolysis. So we're going to flip over really quick and watch a video. This video specifically, it is by a YouTube channel called Science Fix. And I really like the way they design this and show you the electrolysis of water process.
In that small plastic container are 2 metal push pins, and they're inserted a distance that's between the positive and negative lead of the 9-volt battery. So you just insert them in there and make sure that they're that distance apart, and that should be fine. In the container is going to be some water that has baking soda mixed into it. The baking soda in the water allows electricity to flow between the 2 metal tips of the push pins. And so now you set them on the leads, and the electricity can flow between the 2 push pins now. And so electricity is flowing through the water, and so that's enough energy to break apart the water, make it undergo a chemical reaction, so that the H2O gets broken apart into H2 and O2. It's going to be hydrogen gas and oxygen gas. And both gases are going to flow up through the test tubes. And one of the gases is going to be in one test tube, and other one's going to be the other one. How do you know which one's which? Well, if you take a look at the amount of gas in each test tube, there's going to be twice as much hydrogen gas as oxygen gas. So you can see in the right test tube, you have twice as much hydrogen gas as oxygen gas. This is how experimenters first learned that the ratio of hydrogen atoms to oxygen atoms in water is 2 to 1. It's 2 to 1 ratio, thus H2O.
Of course, we can also electrolyze other things, but that's just a really nice example showing the difference for water and oxygen. And I didn't realize it was still drawn on, I apologize. What's shown here is the same picture of what we just saw in that video, where we see that the oxygen versus the hydrogen's being generated at a rate twice as fast as the oxygen. No surprise, right? We're producing 2 moles of hydrogen gas for every 1 mole of oxygen gas from 2 moles of water. So an electrolytic cells do use DC electricity to produce a chemical change. It forces the current in a non-spontaneous direction. So as we saw in the voltaic cell, our electrons, electrons, and I apologize, this picture is from your textbook, and I don't like it. Normally I always draw the anode on the left and the cathode on the right, but we see here they've drawn them opposite on that to try to match the pictures. Here we see that the anode to the cathode, anode is oxidizing, releasing electrons, or producing electrons, right? Oxidation is lost. The cathode, we're using up electrons. On the other side, our anode, producing electrons. Our cathode, consuming electrons. Complete match. We see our electrons traveling from our anode to our cathode. We see our electrons traveling from our anode to our cathode. So, again, anode is always oxidation. Cathode is always reduction. Electrons travel, anode to cathode, always. That does not change. What we do see here that has changed is the sign on the system. At the anode, it is negative in a voltaic cell. The cathode is positive. In electrolytic cells, however, the anode is positive and the cathode is negative. And that's kind of going back to the little chart we drew up here, showing you that the biggest difference is the sign change here, which is what's causing the system to work in the opposite direction. So, how can we figure out what's happening? Well, if an electric current is applied to a mixture of substances, you should be able to consider every substance present to be able to tell me what's actually being oxidized, what's being reduced. You should be able to look at a standard cell potential table and tell me what's going to happen at each point. So, which substance will be oxidized, which will be reduced? Well, the substance being oxidized is the substance that's easiest to oxidize. What does that mean? What does it mean by being the strongest to oxidize? Well, oxidize wants to lose electrons, right? So who's the most willing to lose an electron? The strongest reducing agent. Which substance will be reduced? Well, just the opposite. The substance that's easiest to reduce. Which is the strongest oxidizing agent present. So, again, we can memorize the chart, we can memorize the patterns, but I want you to think through. I don't want you to memorize things. I want you to think about why. What is going to be easiest to oxidize? What does oxidation mean? It means lose electrons. Who's most willing to lose an electron? Let's look at the two extremes of our table here. F2, or if these are written as reduction potentials, so being oxidized would go the opposite direction, I apologize. F minus or Na. Who's more willing to lose an electron? Well, sodium, right? Sodium's much more willing to lose an electron than fluorine. Fluorine gained it. It's not giving it up if it doesn't have to. So on this table, that would be my sodium. It's going to be easiest to oxidize. It is the strongest reducing agent. Which substance will be reduced? F2. Fluorine wants those electrons. It is an oxidizing agent. It is willing to take those electrons and reduce itself. It is willing to bear that, right? To bear that, to take those electrons from someone else, to steal those electrons so that it can be an F- charge. So we should be able to predict that looking at these things. Let's look at this first question. What will happen at the cathode if an aqueous solution containing lead 2 plus, nickel 2 plus, and silver plus ions is electrolyzed? Well, let's see. First, we got to find all these things. I don't know which color will actually show up. Let's see. Lead 2 plus. Here it is. Nickel 2 plus. And I know silver's around 0.8. Yep. Silver plus. So, I want to consider every substance present. Now, when I say every substance present, I have lead 2 plus ions, I have nickel 2 plus ions, I have silver ions, and I have water. Water is also present. Now I have to look at the reduction potentials for each species. For lead, that is negative 0.13 volts. Nickel is negative 0.23 volts. Silver, positive 0.80 volts. Water, negative 0.83 volts to form H2, or positive 1.23 volts to form O2. It's kind of a weird thing to think about. What I want you to think about is all these on a number line. I've got positive 1.23 volts, positive 0.80 volts, negative 1.13 or negative 0.13 volts, negative 0.23 volts, and negative 0.83 volts. And no, these are not drawn to scale because I can't fit them all. But when I'm electrolyzing something, the solution, we work with what we call a working window. We don't want our solvent to break down. Here, our water is our solvent. So we're going to try to stay in a window within that range to keep it from breaking down. If I go to too high of a potential or too low of a potential, I will break down water. But I don't want to. I want to try to plate out these substances instead. And so by doing that, it's going to give the one that wants to be reduced the most is going to plate out first. The one that wants to be reduced second will be played out at second. The one that doesn't care as much will be played out third. And eventually, if I run the potential out too positive or too negative, I will actually break down water and form hydrogen gas or oxygen gas. But what wants to be reduced the most out of the three that actually are metals and would, not part of our solvent, we would plate out silver as silver first. We would plate out lead 2 plus to lead solid second, and again, this is plus an electron. 2 electrons. And nickel would be third. Outside of this window, I would then break down water. But first silver, then lead, then nickel will plate out. What if I've got other species going on, though? What's actually going to happen here in solution? I'm going to think about all reactive species. What I mean by that is what's actually existing in solution. I'm going to think about all the possible reactions that occur, and I'm going to think about what their oxidation reduction potentials are. So if I look here at NaF, I've got an aqueous solution, NaF. That means I have sodium ions, fluoride ions, and water. Every substance present. The sodium, the fluoride, and the water. If I look here, I see, and it's kind of like you're starting at 0 and going out either direction to see what you're going to hit first. Or you can write these reactions down. Another way to do it is to write the reactions down kind of into a table form. Think about every reaction that's present and pick the correlating most positive oxidation potential and most positive reduction potential to see what's actually going to happen in solution. What do I mean by that? Well, I know if I have sodium plus, if it gains 1 electron, it can form sodium, negative 2.71 volts. Fluoride, I need 2 fluorides, form F2 plus 2 electrons. I flip the reaction around, that would be negative 2.87 volts. Water, on the other hand, can form oxygen gas at 1.23 volts and can form hydrogen gas at negative 0.83 volts. These two potentials fall into line much better than the sodium or fluoride do. So what's going to actually happen is at the cathode, I'm going to form hydrogen gas. At my anode, I'm going to form oxygen gas. I'm not actually going to do anything to the sodium or fluoride here just because their cell potentials are so far past the what we call your working window for the solvent you're using. Let's look at this example. Similar example, sodium bromide. What is formed at the anode and at the cathode when an aqueous solution of sodium bromide is electrolyzed? It's not specifying conditions here. So if we are under specific pH conditions, it can change things a little bit. Like a pH of 7 has a slightly different reduction potential than what's shown here for water. If it's under standard conditions, it doesn't specify if it is. If it's not under standard conditions, these things can change. It's not specifying that it's under standard conditions, but it's not saying it's not. So we are assuming it's under standard conditions. I'm thinking about every species present. I have sodium, I have bromide, and I have water. I know sodium's there, bromide, and our water. So what's actually going on here? Well, let's think about what possible could happen at each spot. Let's think about my cathode. Cathode is reduction, which is gain of electrons, okay? Sodium can gain an electron, forming sodium solid. The reduction potential for this is negative 2.71 volts. Br minus can't do anything. It cannot gain more electrons, right? Bromine can only gain up to 1 electron, forming a Br minus charge. It can't gain more electrons. And water, we can have Water forming H2. So water, let's see, hold on, let me write the actual reaction here. Water can gain 2 electrons, forming H2 gas and 2 moles of hydroxide at negative 0.83 volts. I'm going to compare these two numbers here, and I'm going to pick which one is more positive. The more positive one is the one that's actually going to happen. Which means at my cathode, I will form H2 gas. So I'm going to shrink this, and I'm going to do something similar for my anode. Oops. Sorry guys, I'm so used to screenshotting stuff that's what I automatically go to. Now let's think about the anode. Oxidation, lose electrons. Sodium plus can't do anything. It's lost all the electrons it can lose. Has no more valence electrons to lose. I mean, it has core, but it's not going to lose those. I could take 2 bromide ions, because again, you've got millions of them in solution, right? More than millions, truthfully. And form Br2 plus 2 electrons. That would have a cell potential of a negative 1.09. Why negative? Because I flipped the reaction around. I could take 2 moles of water and form 1 mole of oxygen gas, 4 moles of H plus, and 4 moles of electrons. This would be negative 1.23 volts. Now I'm going to compare these two numbers again, and I'm going to pick the more positive of the two numbers. If you pick the more positive, you will always be picking correctly what's being oxidized, what's being reduced. So at my cathode, I am forming H2 gas. At my anode, I am forming Br2 liquid. It's kind of another way to do it instead of thinking about like the number line per se. And when I mean number line is I mean like starting at 0 and going both directions and seeing which one you hit first. This is the other way to do it. You can think about what's going to happen in solution and pick the more positive cell potential each time, and it will get you the right answer. Let's do some more examples. What is produced at the anode when nickel bromide aqueous is electrolyzed? So again, that means we've got nickel ions, bromide ions, and water. At my cathode. And you may have to refer back to a table or pull up a table to get these values, but like here we've got nickel, bromide, and water. So I've got the values written down on the side, but you may need to refer to a table to get these values. If I have nickel 2 plus gaining 2 electrons, forming nickel, that's negative 0.23 volts. Br minus can't do anything. And H2O can form H2 gas plus some other stuff, right? We've got, where is it? Here, H2O plus 2 electrons. See, I don't have the reactions memorized. Giving me H2 plus 2 moles of OH minus. Cell potential here, negative 0.83 volts. This is the more positive. Cathode. I'm going to be forming nickel. At the anode, I need to move this up a little bit. Nickel 2 plus cannot do anything. A higher oxidation state is not listed for nickel. It does not want to lose any more electrons. Earth. 2 Br minus forming Br2, negative 1.09 volts. Water forming O2, negative 1.23 volts. Again, it's kind of like putting on the number line, going from 0 and going either direction, picking the most positive and most negative, or we can use the reactions that are listed on the table, flip them around, and see what's actually going to happen. So at the anode, I will be forming Br2. NABR, I already did this one, I apologize. I forgot that I have this in here twice. MnI2. What about when we have molten? Molten means melted. It means no water. I realize this is not the same exact one. I have to use some kind of picture on it though. But molten MnI2. My cathode. Mn2 plus, giving me Mn, negative 1.18 volts. I minus, can't do anything. It's already got all its electrons. We don't have to compete with water. At the anode, I minus, giving me I2. Again, these are not balanced. You got to write your electrons in and stuff like that, but negative 0.54 volts. So at the anode, I2 is formed. The cathode, Mn is formed. What about when FeSO4 is electrolyzed? It does say aqueous, which means water is present again. Cathode. I have Fe2 plus going to Fe solid. Again, this is not a complete reaction. I have not written the electrons in here. I'm just doing it to save time. But you should be writing it all in if you're actually practicing these. Negative 0.45 volts. What about that SE4 or SO42 minus? Well, I could have 4 moles of hydrogen, or 4 moles of H plus, react with 1 mole of SO42 minus to produce H2SO3. 20 volts. Water also goes to H2 gas. Lots of things going on here. Fe is the main product, so this one can get kind of confusing. Fe solid is actually the main product. At the cathode. Some H2SO3 is going to be formed at standard conditions. Remember, standard conditions means that every concentration is 1 molar, but not much. Very little is actually going to form. At your anode, you can have Fe2 plus going to Fe3 plus. Don't forget that one. 0.77 volts. SO42 minus, can't do anything. The sulfur, let's just write S, I apologize. S is in +6 oxidation state already. Can't go any further. H2O could form some oxygen, negative 1.23 volts, but this is going to be preferred. So, at your cathode, you're going to be forming Fe solid with some H2SO3 being generated. At your anode, you're actually going to be forming Fe3+. What about when I have acidified aqueous sodium sulfate? What does acidified mean? It means that I have extra H pluses floating around. What can happen at the cathode? Let's see, I've got sodium ions, I've got protons, got sulfate ions, I've got water. So my sodium ions can go to sodium, negative 2.71 volts. My protons can go to hydrogen gas at 0 volts. My sulfate can react with protons, forming H2SO3 at 0.20 volts. My water can form hydrogen gas at negative 0.83 volts. Most positive one here is the formation of H2SO3. My anode. Na+, can't do anything. SO4 2- can't do anything. Again, sulfur is already at a +6 oxidation state. Can't do any more. My H2O can go to oxygen. Negative 1.23 volts. H+, can't do anything. So what I find is that at my cathode, I'm forming H2SO3, while at my anode, I'm forming O2.